in the foundations of spin physics and polarization effect in heavy ions. So the stage is yours.
Thank you very much. First of all, I would like to really thank warmly Masoud Shokri, who organized this workshop, very interesting workshop, and invited me to give this talk. And I'll be reporting about recent developments, as the title suggests, in the statistical field theory, which were mostly inspired by the phenomenological observations of spin in heavy ion physics. I would like to acknowledge the crucial contribution of Matteo Buzzegoli, Andrea Palermo, Gabriele Inghiriami, and Yuri Karpenko in what I'm going to say, who collaborated in this work, which took place over the last year in the pandemic, so in complete isolation, almost complete isolation, I would say. And so this is the list of the topics I'll bring up. So I will introduce the motivation of the phenomenological motivations of this this theoretical topic, which essentially is spin, the phenomenological issues which emerged over the last few years, and then I will talk about the possible solution of the so-called spin local spin polarization puzzles, as observed by the star experiment. And then I will conclude by suggesting, if I have time, a measurement of which is related to spin, in order to highlight the local parity violation in QCD. So the introduction is concerning so that what phonological motivations, as I told, were mostly due to the observation of polarization in heavy ion collisions, peripheral heavy ion collisions, high energy. This phenomenon was the idea, the possibility of a global polarization of particles in heavy ion collisions was put forward in 2005 by Liang and Wang. A method, which a theoretical approach based on a spin orbit coupling and QCD inspired, say, collisional calculation. In the 2008, we in a sense amended these calculations by suggesting that polarization could be calculated by using the same paradigm as the hydrodynamics, the hydrodynamic model of the plasma, namely that assuming the proximity to local thermodynamic equilibrium, this gives rise to a statistical, say, statistical mechanics based prediction of the spin polarization, which was much less than this the original prediction. So the idea is that the angular momentum, which is deposited by the two incoming good colliding ions in the quark-gluon plasma, gets transferred because of this of the equipartition, say, of this conserved quantity to the particles, and the particles then should be expected to be polarized along, on the average, along the angular momentum direction, which is the direction orthogonal to the reaction plane. So this phenomenon was discovered in 2017 and is attracted a lot of attention, especially and also by the broad audience in general. Then it was awarded the Nature cover with the title of Subatomic Swirls, because that the prediction, apparently, the prediction of hydrodynamics, which say in the statistical mechanic model, the spin is proportional to the vorticity, of the thermal vorticity, to be precise, of the QGP at the hydrogenization stage. And the prediction was fulfilled, especially the fact that the measurement was in agreement with the prediction, especially the fact that lambda polarization have the same sign, or almost the same, as you can see from the original plot by star collaboration. And this means that this phenomenon cannot be say driven by a mean field, which is charge conjugation odd, like the electromagnetic field, but is favors, because this observation that lambda and anti-lambda have the same, essentially the same polarization, favors the thermodynamic and equipartition interpretation. So this is an updated comparison that Mike, Lisa, and I published in this paper, with the comparison between the measurements updated to 2020 of the STAR collaboration and Alice as well, and these lines show the prediction of the several models, but all of them, it should be emphasized that all of them, what they do is they predict different amount, or say they have different methods of predicting the thermal vorticity, but eventually all of them use the same formula to connect the thermal vorticity to the spin. And it looks like that this, say the prediction is fine, so that all the data and the model are in good agreement, very good agreement, I would say. But then later, some discrepancy came out, and this was concerned with the polarization as a function of the momentum. So the theory predicts the amount of polarization as a function of the momentum of the final hyperon, of the final particle, which is essential in the for experimental reasons is the lambda hyperon. And I think that more will be said about that by Mike in the afternoon. So that this shows that the theory and the theory prediction based on the formula and the observation are in stark disagreement. You can see that this I drew sorry, I drew here a line showing the prediction of the polarization along the angular momentum, so in the direction orthogonal to the direction plane as a function of the angle. And you can see, of the azimuthal angle, you can see that the theory predicts an increase, and the observation, on the other hand, predicts that the polarization is maximal for particles with momenta lying on the reaction plane instead of orthogonal. And similarly, the longitudinal polarization, so the direction of the spin vector along the beam, is predicted to have a sort of an oscillating behavior like for the elliptic flow. And you can see that this is observed in the data. However, the sign of these oscillations is opposite to what is predicted by the hydrodynamic model, and not just by the hydrodynamic model. This is a prediction which say was common to other approaches like MPT and others. So this is was concluded in 2019 that this was not the effect of the decays, namely the fact that the lambdas are also produced, or most of the lambda, I would say, are produced by decays of higher lying states like sigma naught and sigma star. So this was not the problem. And so how to solve it? And there were very many proposals. So this stimulated a lot of work, and I apologize with those who are not listed here because many people participated in this effort with different ideas. So that there was approach of, say, attributing this to a final hadronic interaction or the scattering effect, or to dissipative corrections, namely that, say, the formula that I have mentioned, as we will see, it's a local thermodynamic equilibrium formula, so it does not take into account the possible effects of dissipation. And so there are many authors, say, proposed hydrodynamic with the dissipative effects of spin in it. Or say maybe this another idea, which is more say radical, is that maybe that there is no local equilibrium after all, and therefore we have to resort to a kinetic theory in order to make a prediction of the spin polarization. Also, many people wrote very interestingly, stimulated a lot of theoretical progress in this field. And finally, this is the most, say, I would say, drastic and also fascinating in a sense explanation, is that maybe there is a fundamental role of the spin tensor, which in quantum field theory, which and this is the phenomenon which is able to highlight it. So many people, say, as I said, also participated in this, say, in this theoretical investigations, and they are among the audience. So how, in order to, now what I'm going to say is something different. So what I'm going to tell you is that this maybe, so that is, at least the comparison with the data suggests that this is an effect of an overlooked term in the local thermodynamic equilibrium. So in order to explain this in more detail, I need to go through the basic, say, steps of the theory, theoretical calculation of the spin polarization, which involve, of course, interesting elements of statistical field theory. So how to calculate polarization of relativistic fluid? Well, that basic tool is the covariant Wigner function for the free Dirac field, which is written here. So it's essentially a Fourier transform of the two-point function of the spin 1/2 field, the Dirac field. And it's important to point out that this, triangular brackets involve the mean with, so the calculation of the mean with a density operator. And density operator plays a crucial role, as you will see. So this allows to calculate, so by this approach one can calculate, but when calculate the spin density matrix for a spin 1/2 particle for the single, so what is the spin state, in a sense, of a spin 1/2 particle emitted by the system, and this is given by this formula, which involves the spinors, and momentum P, and the Wigner function. So, and this leads eventually to the calculation of the mean spin vector, which is what we can mainly measure in these conditions, and this is given by three equivalent formulas you can see involved in the Wigner function. So one has, say, either the so-called axial current density in phase space, which is written here in the form involved in the Wigner function, or say different forms in which you have the canonical spin tensor in the phase space, or this simply the trace of the or simply these trace products of the sigma, which are the generators of the angular momentum. Oh, sorry, the generators of the Lorentz transformations in the Dirac field representation. So, but the crucial point here is what is the density operator. So in order to evaluate the Wigner function, we need to specify what is the density operator that is used to calculate the mean. Okay, and in this respect, there is a theory which dates back to the 60s, 70s, developed by Zubarev and the Dutch group led by De Groot, which essentially allows to write down a density operator which is appropriate for local thermodynamic equilibrium. So I want to stress the fact that in order to calculate the spin, one needs a quantum statistical approach, because spin is inherently is a quantum object. Therefore, we need to write down a density operator which is appropriate for the system. And then what we can do in a relativistic framework is that we can write down a density operator representing local thermodynamic equilibrium in a covariant form. And this is written here. So this operator is very important, crucial ingredient, is obtained by maximizing the entropy in the form of the von Neumann entropy, which is the most general we know in quantum physics, by constraining the energy density and the momentum density to be given, okay, and the charge density, if there is a charge density to be conserved, if there is a charge current. In this say formula, beta and zeta are Lagrange multipliers, so they are primordially defined in a sense in this formula, and their relation with the flow velocity and the temperature field are given by this formula, and the chemical potential. Okay, so the map in this approach, the map goes from the left to the right. So in a sense, first comes beta, then comes U. Okay. But if you want to map this to the traditional hydrodynamics way of thinking, that is the formula relating beta and the full velocity. So I would like to mention, since this was mentioned yesterday also, that this method also provides a natural definition of a frame. And this frame, this was mentioned by Michał Spalinski. In this frame, indeed, there are corrections to the energy density of the form that has been, let's say, suggested by BDNK. Okay, and they can be calculated, and the Kubo formula can be obtained, by the way. Now, now the point is the following. So this is the local thermodynamic equilibrium density operator, but this cannot be the true density operator. The point is that the true density operator, that operator that you have seen, depends on time specifically. So in general relativistic language, depends on the hypersurface, which is chosen at different, say, at different stages of the foliation. So this the general relativistic language. It is time dependent, in other words. And so, but in quantum field theory, the true density operator cannot be time dependent. It must be fixed in the Heisenberg representation. So what is the fixed density operator for the system? The fixed density operator is for a system which at some stage reaches local thermodynamic equilibrium, and this is what we believe it happens for the QGP, is given by the local thermodynamic equilibrium at the initial hypersurface. And the initial hypersurface is drawn here, is the, schematically, it's the hyperbola in Bjorken time, where we believe that the quark gluon plasma reaches at the famous tau naught, reaches local thermodynamic equilibrium. Okay, so this is the true density operator. What we can do, we can transform by using the Gauss theorem this density operator so this integral to the sum of the local thermodynamic equilibrium at some later hypersurface, some later time, and we can choose, for instance, say if you want, the freeze-out hypersurface, and this is a very appropriate choice for the problem at hand, plus the integral of the divergence of this object within the space-time region, which is encompassed by the initial local thermodynamic equilibrium hypersurface and the freeze-out hypersurface. This approach in the Zubarev, de Groot et al. Theory allows to nicely separate what is dissipative from what is non-dissipative. Everything which is calculated with this local density operator at present time is non-dissipative. What is calculated by including corrections due to this term is dissipative. Okay, and I would like to mention something which is very important, that this approach was used to derive the first Kubo formula of the shear viscosity in 1983 by the Japanese Hosoya et al. Okay. Now, incidentally, when does this local equilibrium operator become a good, say independent of time? This happens when the divergence of this integrand, so d mu beta nu minus g mu, is 0. Okay, and this happens provided t mu is symmetric when beta fulfills this equation and zeta fulfills this equation. This is trivial, should be constant, this scalar. This gives rise to a non-trivial solution, because this is the killing equation, okay, in flat space-time. And the general solution is known, is beta equal b plus omega mu x nu, where b and omega are constant. So the density operator in this case, if you now plug this in, becomes a combination of conserved generators of the Poincaré group, the translation and the angular momentum boost operators, plus possibly some conserved charge. Okay, so we have that the most general form of global thermodynamic equilibrium in flat space-time depends on 10 constants, which are conjugated to 10 conserved generators of the symmetries. Now, we don't have this global equilibrium in QGP, so we have to make an approximate calculation. Okay, exact calculation would be, if you wish, in this same approach, would be with the exact density operator, of course, but we can't do that. So it's too difficult. So because it involves, knowing the dynamics of QGP, of course, which is non-perturbable, so we cannot do that. What we can do is we can approximate with local thermodynamic equilibrium, as we do for instance, calculate spectra of the hadrons in its simplest form. So let's approximate then rho with the local equilibrium part at the sigma freeze out, hoping that this dissipative part is negligible. This is a hope, which is not just a hope, it's something which is borne out by the observations made over more than 20 years, okay, that we have approximate thermodynamic equilibrium for the abundances, for the spectra, and so on and so forth. Therefore, we hope that this is also applies to the spin degrees of freedom. So in this case, the Wigner function is given by just the local equilibrium part. And now what we have to do in order to calculate it, we have to so we are we face this problem where we have to calculate the trace of this of the Wigner operator with this density operator, exponent of this combination. Now, beta and zeta are not are functions which you can calculate with some hydrodynamic model at the freeze-out, but after all, they are very complicated, and in order to make a simpler calculation, you have to introduce more approximations. A very reasonable approximation is the hydrodynamic limit. So we know that there is a variation of scales, namely that beta changes on a, say, more slowly, on a longer scale with respect to the microscopic interactions or the microscopic lengths, say, relevant to this problem. Therefore, what we can do, we can expand in a Taylor series beta from the point where the Wigner operator is to be calculated this way. So with a first order approximation, what happens with the first order, say, expansion, Taylor expansion, okay? So what happens is the following, is that if we retain only the zeroth order of the expansion, then what we have is simply that once you plug this into the integral, you get beta times the integral of t mu nu of this operator over the hypersurface, which is but the total for momentum, because this is conserved. Therefore, we have beta nu x p nu, and then we obtain what is called the ideal approximation. Okay. If we retain the first order term, so the first order derivative of the beta field, then we have, after, say, separating the symmetric from the antisymmetric part, then we have this combination. So we have a symmetric, so we have the antisymmetric derivative of beta coupled to the angular momentum operator centered in x. And then we have a symmetric part, which is the combination of the symmetric derivative of, we have a combination of symmetric derivative of the beta field, which vanishes in case of global equilibrium, times this integral, which is not the angular momentum, but is a symmetric combination of x and t. So we have these two operators and these two, coefficients, functional coefficients. Now, so we can write this formula in more compact form by introducing the tensors omega and psi, which will be used in the following. This is called thermal vorticity, as you know, that this baby has become popular, and this we call thermal shear, say, to be, in order to preserve the analogy in the naming. This is the symmetric derivative of the four temperature, and they are both adimensional in natural units, so they're very useful because their magnitude can tell you whether, say, this approximation is good or not when you expand the exponent. So in fact, the exponent must be expanded, but otherwise we are not able to so we cannot make an exact calculation unless there is a global equilibrium. And so in order to obtain a prediction, a quantitative prediction, one can use an expansion of the exponent that is called linear response theory if this is stopped at the leading order. And then what we have is that we have two terms, A, which is beta dot p, so this is usual thermodynamics, and then we have B, which is a combination of angular momentum multiplied by thermal vorticity, and this tensor Q multiplied by thermal shear. So now we can calculate the Wigner function with the linear response theory and obtain some expression, and this expression essentially is known once you can calculate the thermodynamic equilibrium at the traditional thermodynamic equilibrium, the correlators of Q and the Wigner operator and J and the Wigner operator. So this eventually leads to a formula for the spin polarization vector after after some maths. And in the past, what happened, say, for instance, we did that. We neglected this term, so this linear term in the symmetric derivative of the beta field, simply by prejudice. And the reason was that the formula, for instance, the formula of the spin, they involved a Levi-Civita tensor. And my first thought was, okay, the Levi-Civita tensor contracted with xi mu nu is 0 anyway, so this won't contribute to the spin polarization. And so that what we did, we retained just, or we confined ourselves to this term, which survives a global thermodynamic equilibrium, by the way, and obtained this formula, which has then been used to calculate phenomenologically the spin polarization. Okay, and then this formula was confirmed by other approaches that I have listed here. Now, the point is that there is a combination, a contraction of momenta, thermal shear, and Levi-Civita tensor, which does not vanish. So, surprise, thermal shear does contribute indeed. And including this neglected term and applying linear response theory meticulously, one can obtain this formula, which is the correction of, so which is a new term relating the spin polarization to the thermal shear, namely to the linear order gradients of the beta field. It involves a contraction of psi with the momenta and a Levi-Civita tensor, which does not vanish. This formula was obtained, although not by using this method, with a different method, of course, but this bears out to say the validity of this of our finding, that by different method in a almost simultaneous paper by Liu and Yin 3 days before, we realized that they did the same, that the which was published with a completely different method, I would say. So I don't know the details, so if one of the speakers is there, maybe can clarify. It is important to stress the fact that this formula depends on a specific vector. In this case, the specific vector is the vector, the time direction in the QGP frame, and only the QGP frame, I would say. So this is only apparently, say, breaks covariance. This is a specific vector, which is related to the shape of the hypersurface, which is, say, used to calculate this, say, which appears in this problem. The hypersurface is the freeze-out hypersurface in our case of QGP, and this term and this explicit dependence on T should be there because Q, unlike J, is not a proper tensor. It is a tensor only once the hypersurface is specified, but otherwise it is not. And it is not because the divergence of the integrand is not 0. Therefore, one can show in, say, relativistic quantum mechanics or quantum field theory that whereas J mu nu transforms a proper tensor under Lorentz transformations as an operator, and this happens because sigma, say, because this integral is independent of hypersurface, Q does not. So Q is not a tensor in a quantum mechanical sense. So it's not a tensor operator, and therefore you say you must have a leftover of this dependence of Q on the hypersurface in the final formula, and this is what is the reason of this vector. So what is this new term? So we were surprisingly, so there is an additional contribution. What one can hope to say, one can say, okay, why was this overlooked? When if you go through this, if you expand this xi in several, say, in the contributions coming from the acceleration field, from the properly called shear tensor, from the expansion scalar, and from the gradient temperature, what is found is that in the non-relativistic limit, so when c goes to infinity, all terms disappear, so they are all relativistic corrections to the spin, except the gradient of temperature, the gradient T terms, which give rise to this correction in the non-relativistic limit. So a correction which says that the particle, which has a velocity v and moves through, say, a system which has a gradient of temperature, gets polarized. There is an equal contribution in the non-relativistic limit for vorticity. I think this is a very interesting phenomenon and should be, say, studied more in detail. Now let me go to the final part of this talk. Let's now apply all of this to relativistic heavy ion collisions. So let's go to phenomenology. So now we know that if we believe in what we have seen so far, that the spin polarization vector is given by the sum at local thermodynamic equilibrium is given by the sum of two terms. The first term is the known one, so thermal vorticity. The second one is related to the thermal shear, so it comes from the symmetric part. So what happens? First of all, so can we obtain a reliable prediction of the spin polarization in heavy ion collisions? Well, we have to check whether our approximation is adequate, and in fact it is, because if you plot if you plot in a histogram, so the magnitudes of the thermal vorticity and the thermal shear, which are adimensional, you see that in most of the hydrodynamic cells they are less than 1. Therefore, it is quite reasonable that the leading order approximation is a good approximation for the calculation of the spin polarization vector. Now let me just remind you. Let me just flash again the local polarization puzzle, so the discrepancy between the theory and the model. And let me now show you what happens with the new calculation. So that is, these calculations were made by the chairman with his excellent hydrodynamic code VHLAE, tuned to reproduce gold-gold momentum spectra at Ricktop energy. And this shows a contour plot showing the dependence of the dependence on momentum of the longitudinal component of the polarization, the spin polarization vector, showing that it becomes negative in the first quadrant. So that's the discrepancy with the data, and then it becomes positive and so on. If we plot, if we plot only the new term depending on the thermal shear tensor, what we see is that now it has the right sign. So it is positive in the first quadrant, then becomes negative. So the sign of the oscillation is the correct one. I mean, it's the one in agreement with the data. However, the spin polarization vector is given by the sum of the two, and with sum of the two, if we add this term to this term, what we obtain is a final pattern which is not in agreement with the data again. This calculation was made in a paper which appeared a few days later, the paper by Liu and Yin, and also confirmed that, and we are in full agreement with their observation. Now comes the last idea, which is that the last idea is to revise the approximation that we have used to calculate the spin polarization vector, because after all, what we expect is that at very high energy heavy ion collisions, the hypersurface, a special one, should be the T equal constant hypersurface. So we do not expect to have local thermodynamic equilibrium sim. What we expect to have in at very high energy is isothermal local equilibrium. So local equilibrium at constant temperature. So thanks. So we have that in the formula that we have developed, that we have thermal vorticity and thermal shear both include temperature gradients. Temperature gradients in the theoretical calculation do contribute to the spin polarization vector, as was shown by Yuri in this paper. So you can see these lines, they show the relative contribution, or the absolute contribution, sorry, of the acceleration, vorticity, and gradient of temperature. You can see that they contribute. Gradient of temperature and acceleration, they go together. This is because we have quasi-ideal hydrodynamics, and for a completely neutral system, grad T and acceleration, they are parallel and they go together. They have the same, they provide, say, the same contribution. Now, but is it the best thing to do? So is it really the best approximation we can make to calculate the spin polarization vector? Because after all, the original formula of local equilibrium says that we have to calculate the Wigner function with this operator. And we have expanded in a Taylor series, the beta field, like this, okay? Well, as I told you, that since the hypersurface is expected to be isothermal, because after all, at very high energy, if we believe that the plasma hydronizes with some thermodynamic condition, okay, at very high energy, the only possible thermodynamic condition you may have is T equal constant, because the chemical potentials do not play a role. So there are, in the core group plasma, you have the two, say, very important thermodynamic quantities to determine all the others, temperature and biochemical potential. But very high energy, biochemical potential is almost zero. Therefore, you only have temperature. So if the freeze-out hypersurface is T equal constant, then this has a consequence of this calculation, because it shows that the calculation that the expansion we have made is not the most appropriate. In other words, what we can do is that since beta is related to U and T from this formula, we can take out T because we have to integrate over the hypersurface. So if T is constant over the hypersurface, why should we expand it? We can take it out and expand only U. This is the basic idea. And then we are left with this formula here, in which some of the contributions related to the gradient of temperature disappear. So the final formula, after, which is very simple to obtain, just remove this gradient of temperature for the previous one, is the one in which one has 1 over T factor out and replacing all the gradients of all the, say, the thermal vorticity and the thermal shear with this the kinematic shear and the kinematic vorticity. Okay, this differs from this formula gives a different quantitative prediction with respect to the previous one. In order to understand the point, so this, when I mean, I had a sort of email exchange with some of you, some people, including some of you who are now listening, that in order to understand the point, because this raised a lot of some question, why should we say remove the gradients of temperature after all? Okay, I would like to give a simple example of a function of two variables in order to explain the point. So let me do this because it's very important. Suppose you have to approximate this integral. So this is an integral involving, so we have functions of two real variables, x and y, in the Cartesian plane, and we have to calculate this integral. Suppose, and this is what happens in most, say, of our calculations, that we have a very peaked function around some point x and not y not on the circle. So suppose that you have this function g is very peaked around some point. So whenever you have this, say, whenever you are in this circumstance, it is obvious that the first thing to do is that, okay, we can expand around x naught, say, the smoothly varying function, okay? And say, someone would say, okay, let's expand e to the exponent of square root of x squared plus x squared around x naught. And then if you do that, you get something which is e to the r times e to the gradient of r multiplied by x minus x0 times g, okay? But this is just pointless if the curve over which you integrate is already something where x squared plus y squared is constant. In this case, you just have to replace here e to the r, which is the radius of the circle, and that's it. And this is a simple case, which is alike to what we have in heavy ion collisions, supposedly at very high energy. So in the previous example, so in other words, if you take this out, because you are integrating over a circle, then you get the exact formula. Otherwise, if you expand R, then what you get is some contribution which can only make the approximation worse. And this is not vanishing. And this is what we probably do if you expand, say, beta and xi instead of u and instead of u. Okay, so similar so it's a very similar case. So all these terms that we have introduced in the expansion of beta, which are proportional to the gradient of temperature, are say can only make the approximation worse if the hadronization hypersurface is the equal constant. So now let me sketch the results. So I'm running out of time, and you can see that if we now use this say new formula in the data, what you can obtain is that you have now restored agreement with the data, and the local polarization puzzle seems to be solved both for the component along the angular momentum and the longitudinal momentum. So this is a very nice fact. Okay. Yes. So this is the calculation showing that the longitude, the component along the angular momentum, and you see that this is now is so the solid line is what you have to see to follow, that this black line compared with the data, although the agreement is not perfect, but anyway, what we see is that now we have polarization which is larger along the reaction, from particle along the reaction emitted along the reaction plane, and minimal when they are emitted orthogonal to reaction plane, and moreover, also that the longitudinal polarization sign is now in agreement with the data. And also, it's very important to point out that this is very sensitive to the hadronization temperature. So the sign of the longitudinal polarization seems to be very sensitive. In other words, by changing the coupling temperature by few tens of MeV, then you get you can also revert again the behavior. So it seems to agree with the data with a freeze-out temperature which is around 155 MeV, which is in good agreement with other, say, with more important, I would say, probes so far. So now I don't have time to. I would have liked really to talk about this proposal of using polarization and local parity violation. So let me just make an advertisement. I don't have time to this paper. So if you have time, have a look at it, because it suggests a measurement of a way of detecting the local parity violation with by measuring spin without the mediation of the electromagnetic field. So let me now jump to the summary and outlook. So I would like first to conclude with a theoretical statement. So quantum statistical mechanics and this approach by Zubarev, originated by Zubarev in the 60s, is an essential tool to properly deal with spin physics in relativistic fluid, and not just spin. Okay. Local thermodynamic equilibrium, we have studied this in detail, and we have found a new and expected non-dissipative term relating spin polarization with a symmetric gradient for temperature, which was independently found in a similar study. This is under further investigation. We have observed that local polarization puzzles, so disagreement between data and theory, can be solved by including this term in the numerical analysis, along with another crucial observation that hadronization happens at most likely at T equal constant. So in other words, the best vorticity or best gradient depends on the hadronization conditions. This is also a conclusion. So what happens at high energy? So what is the best formula at high energy? Maybe it's not the best formula at low energy. Important phenomenological consequences say that of this observation, if this will be confirmed, that local equilibrium seems to hold, so the ideal fluid picture seems to hold in the spin sector too. So spin it's a very sensitive probe, depends on the gradients instead of beta instead of velocity field and T. Depends on the gradients of this field. So it's very and it seems to agree, with the paradigm of the ideal fluid. And then finally, some topic that I hadn't time to mention. So thank you very much, and I'm sorry for having exceeded slightly my time.
Yeah, thanks, Francesco. Very nice talk. So we still have time for a couple of questions. So Uri, please go ahead.
Hey, Francesco, very, very nice. I'm confused about what you said in the last 10 minutes of your talk. If you formulate the contribution from the thermal shear stress or thermal shear tensor, and where you pointed out that this doesn't seem to resolve the problem, but you do the integral over a freeze-out surface which has constant temperature, you can just factor out the factor 1 over t, and you should get exactly the same result that you got in the last part. So did you not do the integral over constant temperature surface?
Yeah, I mean, this is precisely a question that other people ask, and I would like to stress it's not the same thing. So if you if you integrate over some, and the reason is the following: is that when you expand beta, I'll tell you mathematical reason for that. When you expand beta, what you do is that you make a Taylor series in the Cartesian coordinates. So the gradient of t is not 0 on the hypersurface. The gradient of the gradient of t is normal to the hypersurface. So therefore, if you include this in the expansion, and then you integrate over t equal constant hypersurface, you will still have a contribution from the gradient of t multiplied by something in the integral. In order to explain this, this is the reason why I showed these slides. So, with a very simple example, how this can happen, that if you have say a manifold, okay, this is a line, of course, in 2 dimensions. It's very manifold over which this quantity is constant. Okay, you can expand this in the Cartesian plane. Okay, and you get this. Can you follow?
Yes. Okay, I'm following, but not intuitively.
No, yeah, no, I know that it's not intuitive. This is why I try to convey the message with a simple example. The point is that you are not expanding when you make the expansion of beta and you have the gradient of temperature. You're not expanding along the hypersurface in the coordinates of the hypersurface. You're expanding in Cartesian coordinates.
Okay, I think I get your idea, but have you done the following exercise? You start from the thermal shear, and then you just write beta as u over t, and you write it out in the different terms, yes. And then then there should be extra terms that involve the gradient of t that somehow don't vanish even if the temperature is, even if the surface is isothermal. No.
Absolutely. I mean, this exercise was implicitly was done, in fact, by comparing these 2 plots. So what we did is that if you take these plots, which were made by the chairman, show that if you sum up these 2 terms, okay, where you have the gradient of temperature in there, right? So this is thermal shear plus thermal vorticity. Look at this pattern, okay? This is the integral over t equal constant hypersurface. So the chairman calculated these fields with t equal constant. Okay, it is in fact energy density constant, but then he plotted that this is t basically constant. Okay, because that at 200 GeV there is no difference. So that energy density equal constant is equivalent to t equal constant. Okay, this is the result of including the gradient of temperature. Okay. Now, this is the result, numerical result without it. And they differ, they do differ. Okay. There is only one mathematical case in which they have to give the same result. And this is when the hypersurface is a hyperplane. If the hypersurface is a hyperplane, then the 2 calculations will be exactly the same. But the hypersurface t equal constant is not hyperplane. It is a
okay.
Hypersurface.
Okay. Yeah. Thank you. Let's have somebody else also ask.
Yeah. Please, Giorgio, go ahead. Maybe make it quicker. We are running out of time.
Yeah. Sorry. Yeah.
It's me.
Yeah. Go ahead. Yeah.
I didn't hear that you were calling me. From a phenomenological point of view, I mean, this is really impressive. I mean, this isothermal, which is physically sort of reasonable. But when you were in the beginning, you were comparing and contrasting, unequilibrated spin with angular momentum, which is kind of it's necessary for causality. There will be talks about this at this conference, that causality impedes local equilibrium between spin and angular momentum. But the thing is, as you showed that in the Taylor expansion argument, G mu nu is a generator of the local Lorentz group. Q mu nu is not even a tensor. And moreover, you've done two expansions here that don't necessarily commute with each other, I think. The Stokes theorem expansion around local equilibrium and the Taylor expansion around flow, So are we sure that what you call the symmetric shear term is really a local equilibrium term rather than a manifestation of spin and flow, rather than something similar to what other people are calling diffusion of spin around flow, lack of equilibrium of spin around flow?
Well, I mean, actually, this is it's not an easy comment to work out. I mean, I would say. Then, I mean, I don't know if I got it, but say this
equilibrium is sort of around conserved quantum numbers, and Q mu nu is not a tensor.
Okay.
Yeah.
Okay. Let me say this. Okay. That the definition of local thermodynamic equilibrium is something that several say approaches. They provide several definitions. Okay, so for instance, kinetic theory, the definition of local equilibrium is different when the collisional integral vanishes. In this case, in this approach, that I believe is the most fundamental for this kind of systems.
I agree.
Because it is quantum based. Okay. In this case, the definition of local thermodynamic equilibrium is when the von Neumann entropy is maximized with constraints of conserved densities, not conserved quantities like energy moment, conserved densities. And this gives rise to this term. Okay, the fact that you have enforced the maximization of entropy with conserved densities allows, in a sense, it's the ultimate reason why we have this say thermal shear term. Okay, in this approach, there is one thing which is extremely clear. So without no ambiguity, the classification of what is say dissipative and non-dissipative. This is absolutely clear cut.
Sure.
You cannot get it wrong.
Yeah, but
Okay.
And then anything that sorry.
We're basically running out of time, so
yeah.
maybe
So I
got around the break. So at 3:45, if it's possible.
Yeah, absolutely, yes. Thank you very much.
S-
Thank you, and
s-
sorry
sorry,
for taking extra.
sorry, that's
it's not
I
a
mean-
simple question. I agree.
Yeah,
We've been
I
arguing about
understand.
this for a while. Yeah.
I would be also very interested, but maybe Wojtek, if you had a comment, maybe you just vocalize the comment and then we move to the other speaker.
My first comment is, okay, can you hear me? I hope so.
Yeah.
Okay,
So
my first comment is that this grade is, hi. Good afternoon, good morning, good evening to all participants. I think this gradient is essential because we have to include it, because I think the contribution from the gradient is exactly equal to other contributions if you use hydrodynamic equations. So this is one comment. The second comment is that you mentioned, or you wrote in the slide, that you are consistent with the paper by Fu. I disagree with this. I studied these two papers and I think you have different terms. My third comment is that Fu et al., they didn't describe actually the data, because if they use the physical mass of the lambda hyperon, they cannot describe the effect. So they make this trick, and they say that actually polarization comes from the strange quark, and they artificially decrease the mass to get it right. So I think this is just, numerology. I think this is not, I would say, valid what they do. So to be short, so these are three comments.
Sorry, I don't know if I have to answer the comment. Let me say, I mean, I know that. So the point of
Can I suggest to discuss this in the Q&A? I think
Yeah,
this is a very interesting set of questions which require extensive discussion, I think.
Yeah. Please hang around at the Q&A time and also at the break just after the session.
I have to stop the share.
Yes, please. So thanks a lot for the talk. That was very nice, and the discussion was kind of